Hey guys, this is Mr. Ballard, back with Batman Under the Hood, talking about the physics of Batman Under the Hood, of course. Basically, if you don't know, what I typically do is I pick different movies or cartoons and I pick different scenes out and I break down the physics. Today we're specifically going to talk about Newton's laws and energy. We're going to talk about kinematics. We're also going to talk about electricity and momentum and impulse, of course. We're even going to touch base on some waves. If you're not quite there and you haven't covered all those topics in physics, don't worry. You can always come back to the video and watch it again. But for now, let's see. Again, what I like to do is I like to show the video first, and then we break it down. So let's see the first scene in Batman Under the Red Hood. So we got this absolutely brutal scene with the Joker here, and he's beating up on Robin. This is, again, the second Robin. So we got the Joker. He takes this swing, and oh man, that was awesome. You guys want to see it again? Okay, we'll run it back. All right, so basically I want to talk about momentum and impulse when it comes to this scene. If the Joker strikes Jason Todd with a crowbar, which has a mass of about 0.69 kilograms, yes, I actually looked that up, at a speed 32 meters per second, which is about how fast you swing a bat when playing baseball, and after slamming into Jason Todd's skull, which has a mass of 7 kilograms, continues with a velocity of 2 meters per second, what will the final velocity of Jason Todd's head be? And then, of course, after that problem, we're also going to look at what is the amount of force his skull would actually be experiencing if the collision happens within 0.04 seconds. So what force does his skull experience? A typical human skull it basically cracks around 873 newtons. So we're going to see how hard Jason Todd was hit in this problem. So I've got a problem. Now in physics, what I do whenever I get a problem is I identify all of my givens. All right, I use something called the guess method. It's not A, B, C, D, just guess whatever you want. It's identify all of your givens, then point out your unknown, and then once you know those things, you can usually stumble upon an equation that you know you can use, and then you substitute those values in and solve. So let's look at first what are our givens. So we got 0.69 kilograms. Kilograms is definitely a unit of mass. That is the mass of the crowbar, correct? So the first thing I'm going to write down is the mass of the crowbar is 0.69 kilograms. Next we got 32 meters per second. All right, meters per second is a unit of speed, and that's how fast the crowbar is initially going, right? So we got the velocity of the crowbar initial, 32 meters per second. Then we've got the mass of Jason Todd's skull, which is 7 kilograms. So I'm going to write that down, or Robin's skull, I should say. Continues with a velocity of 2 meters per second. So the crowbar continues after hitting his skull at 2 meters per second. So we got the final velocity of the crowbar at 2 meters per second. And the question originally is, what is the final velocity of Jason Todd's skull? Now we know that the original velocity is 0 because he was just sitting there doing nothing. All right, what we're really looking for is the final velocity. So we've got mass, and we've got velocity initial and final of the crowbar, and we've got mass of Robin's skull and the initial velocity of Robin. What we're looking for is the final velocity. So then you have to choose the equation. The equation we're going to use is the momentum equation, conservation of momentum. So we got the momentum of the crowbar and the momentum of Robin's head before, and then we got the momentum of the crowbar and Robin's head after. Now I'm just going to plug these values in to where they go. So we got 0.69 times 32 plus 0 equals 0.69 times 2 plus 7 times our unknown final velocity. So all you guys got to do is solve it at this point. I'll give you some time. We get a final velocity of 2.96 meters per second. So that's how fast Robin's skull is going after it gets hit, which doesn't seem like a whole lot. But what I want to know is how much force is he experiencing after that hit? So now I want to know the time it takes. So I identify my time. So now I know the change in velocity, and ultimately I know the change in momentum, and I know time. So think about what relates those. See if you can come up with an equation for that. Well, if you guys know, change in momentum equals something called impulse, and the equation for impulse, given the symbol J, is equal to mass times change in velocity, which is ultimately the change in momentum, equals force times the change in time. So again, I'm going to plug those values in. So we've got the change in velocity of Robin's skull in his head. Then we got force that we're looking for, and we've got 0.04 seconds. So we're going to just divide the change in momentum by 0.04, and we get a total force of 517.5 newtons. So it's not quite enough to crack his skull, but man, can it cause some serious damage. All right, so momentum and impulse. A little bit about momentum and impulse, all right? Basically, momentum and impulse is considered whenever there is any type of collision or an object ever changes its velocity. One of the real applications of momentum is if you're playing billiards, right? Pool. And you want to make sure that the 9 ball goes into the right pocket. Well, you have to think about the momentum of the first ball, and you got to make sure that you hit it with the right angle. Because not only is momentum conserved in one direction, it's conserved in all directions. Another huge thing for momentum is when you're thinking about impulse as well as momentum, because you want to try to minimize the force a lot of the times in big collisions. That's why you have airbags and things like that. They just give you a little bit more time. That way the amount of force you feel is significantly less. So that was momentum and impulse. What are we tackling now? Oh, well, we got a new scene. Let's see. Oh man, we got Nightwing saved, of course, by Batman. Alright, so here we go. We got the scene breakdown. First you got Nightwing being attacked. But then he turns around and then stabs him in the face. Falls down. Oh, but Batman comes and saves him on his rope. Alright, so basically in order to tackle this problem, well, here's first off the problem. If Batman, after catching Nightwing, who is traveling at a speed of 4 meters per second, fires his grappling hook, which travels 11 meters before wrapping around a crane at an angle of 30 degrees, what will the tension in the cable be as it swings through the lowest point? So as soon as he catches Nightwing, Batman and Nightwing are traveling at 4 meters per second, all right? And then he catches them at an angle of 30 degrees with an 11-meter long rope. Basically what's going to happen is they're going to swing through the bottom, and I want to know how much force, because tension is a measurement of force, is the rope going to handle when it goes through the lowest point. The lowest point is the most important point because that is the fastest point. Why is it the most fastest point? Because conservation of energy. They're going from high potential to high kinetic. So let's look at the actual problem. Let's identify first, again, all of our givens, then our unknown. We're going to choose our equation. We're then going to substitute in and solve, of course. So the first thing we know is 4 meters per second. That's how fast they're originally going. So that would be our initial velocity. Fires his grappling hook 11 meters. We know the distance, but distance might be kind of interesting. We also know it's 30 degrees. What we're really looking for when we're talking about energy is change in height. So we're not looking for the 11 meters, we're looking for how much change in the actual height there is. So basically, he's going to swing down to here, right? We want to know up here to down here, what's that change in height? So the change in height, I could use 11 meters, and then I could just subtract out the cosine, because we know when it's fully all the way down, it's 11 meters long, correct? But if I'm talking about just this height, well, I can just use the cosine 30 degrees of 11, and I can get just this height. And then if I just subtract that height from 11 meters, I know the change in height. So we got 1.47 meters is the ultimate change in height. We know the initial velocity and the change in height. We also were given the combined weight of Batman and Nightwing, 328 kilos. They're pretty muscular dudes, so that makes sense. All right, so we got a combined mass of 328 kilos. We're again looking for the tension, so that's the force, but in order to get that, we also want to know the final velocity. So the first thing I'm going to do is I'm trying to solve for final velocity using energy. So we, at the beginning, of course, have both potential and kinetic, and at the end, it's almost entirely kinetic. So let's write the equation out real quick. We've got the initial kinetic energy of Batman and Robin. We've got the initial potential energy of Batman and Robin, and then we've got the final kinetic energy of Batman and Robin. And ultimately, we're looking for that final velocity. So let's plug in all of those values really quick. We, of course, don't really care about the mass because the mass is everywhere. It's in every single variable, and because it's a repeating variable on both sides, we can just cancel it out. We can factor it out and then just cancel it out. So we ultimately left with 1/2 force squared plus 9.8 times 1.47 equals 1/2 v final squared. And we're looking for that final velocity. Once you move the equation around and you actually solve it, you of course get 6.69 meters per second. So a little bit faster. All right, but again, we're not totally done with the problem. We now know how fast they're going at the bottom of the swing, but let's look at the tension, because that's ultimately what we're looking for. Now, how do we get tension? Well, they are going in a circular motion. All right, and whenever an object travels in a circular path, there always has to be an inward force. And for Batman and Robin, the inward force here is the tension of the rope. As long as the object's traveling in even a semicircle, there has to be somewhat of an inward force. And in this scenario, it is the rope. So that rope has to keep them up. So if I draw the free body diagram, however, I've got tension going up, but you still have their mass, correct? In the end, you take tension minus their force of gravity, and that has to be the net force inward. In order for an object to for an object to travel in a circular path, once you cancel out all the forces, there has to be something left over pointing towards the middle, and that's the net inward force. Some people call this the centripetal force, but I think calling it the centripetal force is confusing because the centripetal force, it's not really a force, it's just like there has to be some sort of tension is the centripetal force here. All right, and so try not to write centripetal force anywhere. It's just understand that there is a force always pushing inward. And in this scenario, that is tension. So we got tension minus gravity equals the net force inward. What's special about the net force inward is it's got acceleration of a circular path, which I can replace with v squared over r. So then I plug in all of my values. I've got the mass of Batman and Robin. I've got their final velocity squared over the radius of the rope, or the path they're traveling in that circular path. And then I'm going to add the force of gravity to ultimately get that tension. So ultimately the tension experienced by this rope is 4,550 newtons, which is actually quite a bit of force. But you know, Batman's always prepared for this kind of stuff. So when it comes to Newton's laws is pretty interesting. It's basically the fundamental understanding of all motion. Once we understand Newton's laws, we can manipulate anything we want. Someone's always like, well, why do you learn physics? The reason why you learn physics is so that you can completely adapt the environment around you to whatever you want it to be. If you understand physics, you know exactly how much energy is needed, all of these different things. Well, that's part one of Batman Under the Red Hood. I'll get back to you guys later with part 2 and part 3. I hope you guys enjoyed the video thus far. Make sure you like and subscribe. I appreciate it. Thanks.